All right, last class was about some application of amortized analysis. This class will be an application of randomized algorithms. So just to recall, a week ago, I think a week ago, was our introductory lecture on randomization. So I defined a bunch of basic things. What is probability? What are random variables? Linear of expectation was a big theme. And we did a few very simple algorithms. We did 3SAT, an approximation algorithm for it. That was just flipping coins for all the variables. We did quicksort, which was you're sorting stuff, but you just pick a random thing, split the input in half, and recurse. And then we discussed a little bit, and I guess you guys are fighting through right now, um, analyzing the quick select algorithm, where the goal is to, I don't know, find a median or something, but the idea is to randomly pick an element, split the data in half or into the two parts, then recurse on one side or the other. So, all right, so that's all good. Uh, so today we'll look at a couple basic problems. We'll look at max sat again. Okay, we're going to try to do even better than we did last time. And then we'll also look at a problem called sec cover, pretty standard, well-known problem. And then maybe we'll discuss covering integer programs, maybe we won't. But really the goal is to use two tools in conjunction. One is linear programs, which we discussed a little bit when discussing max flow because that was an example of a linear program. And then we're also going to combine that with a technique called randomized rounding, which is a pretty simple way to use randomization. And so this approach of combining linear programming and randomized rounding is like a very standard way to approach NP hard problems. It solves many more things besides the things we'll discuss today. So it's a pretty broad thing, and I think it's good to expose you guys to linear programs and stuff like that just a little bit. So, okay, so that's the plan. Let's see, where do we start? All right, so let me explain this general paradigm of using linear programming. Okay, so randomized rounding um, is sort of like a story of well, it's especially useful when looking at NP hard problems. Okay, so we have problems that are polynomial time we can solve exactly, and then we have problems that are NP hard we don't think we can solve exactly, but we still are interested in these problems, and one way out is to try to approximate them instead, and still do it rigorously, try to get some approximation bounds and stuff like that. This tends to also work well in practice. Okay. And it's also going to be a story about the differences between continuous and discrete optimization. So almost all the time in this class, we're actually interested in discrete problems and discrete solutions, right? Like, give me the shortest path, give me the minimum spanning tree, like some yes or no discrete thing. Okay. But discrete problems can be hard, right? Hamiltonian path is very discrete and it's very hard. Okay. Linear programs will be an example of continuous optimization. And continuous optimization sometimes doesn't have to deal with some of these weird things that arise with discrete optimization, all this P versus NP kind of stuff. And we can try to leverage this, that continuous optimization is not cursed by this complexity. All right, so what are integer programs? There are roughly, well, so you guys have kind of seen this implicitly many times before, but maybe not written in this dry mathematical notation. So let me go through it carefully. So it's just a math program of some kind. So the computer is trying to set values to variables subject to various inequalities. Okay. So you might be trying to minimize or maximize like some weighted sum, right? I don't know. Maybe setting xj for a variable is like buying an object and setting it to 0 is not buying it or something, and the c's are costs or something, so you want to get a minimum cost or something like that, right? There's some kind of objective, some quantitative objective that's a linear function, some weighted sum of the variables x's. And in integer programs, I can constrain my variable x's to be integers. You can only let it be 0 or 1 or 2 or 3 and so forth, right? So that's where integer comes in, integer program. And then you describe like your constraints, what x can be, with again linear equations and inequalities. So like, oh, this sum of x's can only be at most 2 or something. Or if you want to say all the variables have to be 0 or 1, I would write, oh, this variable xi has to be at least 0 and at most 1. Right? And I do that for every xi and stuff like that. So, right. So that's it. I mean, at some level, nothing too complicated, right? I mean, inequalities in some sense, I think is less complicated than, I don't know, the rules governing a spanning tree or various complicated combinatorial objects we've discussed, right? It's just like, oh, this plus is less than equal to that. Like, pretty simple. Okay, so those are integer programs. As we'll see, they can be used to model a lot of things we do, and so they're going to quickly be shown to be NP hard. So what are then linear programs? So linear programs we've already discussed, but in relation to integer programs, they're the same thing except we don't require the variables to be integers. So the only real difference is instead of saying x has to be integer valued, we'll say it can be real valued. So it can be any continuous number. So it's not just 0, 1. It can be 0.1, 0.2, 0.3, anything in between. Okay, and that's it. Okay, so the only difference between an integer program and a linear program is that an integer program, oh, I hope it doesn't break. In an integer program, x is required to be an integer. In a linear program, it doesn't. Okay, so not a big deal. That said, just by allowing the variables to be continuous, okay, linear programs are actually all polynomial time solvable. Technically, they're called weakly polynomials, so it's polynomial in the bit complexity of the input. Okay, and it's a very, very important and practical tool. So the first algorithm to solve linear programs is this famous simplex algorithm from 1947, which Danzig supposedly proposed as a homework problem in his class. I don't know. Do you guys know this story? Okay, so Danzig was a graduate student. He was taking some class, and he showed up late to class or something, and he saw these questions on the blackboard, and he wrote it down for homework, and he thought all weekend, and he came back, and he turned it in, and it turned out that these were like the big open problems in the field, and he had figured it out over the weekend. Although he had already like done some related stuff when working for the government during World War II. But I mean, he was doing some optimization. So anyway, so Danzig, there's this famous story about him kind of accidentally solving the simplex algorithm or not realizing how big a deal it was. It wasn't actually a polynomial time algorithm for the problem, but actually it turned out to work really, really well in practice. So, since 1947, operations research people have been using the simplex algorithm pretty reliably. And it's a huge open problem to try to prove that it's a polynomial time algorithm. Like really, really big problem. But the first polynomial time, so in those 30 years, it quickly realized how important and useful linear programs are. We'll see also later today some applications. But it was a huge problem to try to get a polynomial time algorithm for it. So that's not resolved until 1979, when a Russian named Kachyan proposed something called the ellipsoid algorithm. It's based on this thing called John's ellipsoid theorem from high dimensional geometry. I don't know if you guys have been exposed to that. But that was the first polynomial time algorithm. I don't even know if Kachyan actually stated the polynomial. He might not have been so interested. A slightly, considered a little bit more practical algorithm came a few years later in the interior point algorithm. That's our second polynomial time algorithm by Carmarker. The ellipsoid algorithm was I think treated as being very theoretical. It was kind of done by a mathematician using this high dimensional geometry fact. Interior point algorithm looks a little bit more like the convex optimization stuff you guys might have seen before, with like a potential function and stuff like that. Anyway, but the point is, integer programs we can't solve. Linear programs we can solve. I can just assume there's a black box to solve some given linear program. The algorithms themselves are actually quite hard to describe, and it would be very hard for me to prove it to you guys because basically we need like a month of practicing math at a time. So, okay, all right, but it's this compare and contrast that I want to emphasize, right? On one hand, we have discrete optimization. On the other hand, we have continuous optimization. So on the discrete side, we have integer programs and basically everything we've done in this class. And you have this issue of integer programs being NP hard. For linear programs, which don't quite often capture exactly what we want, because usually we do want kind of black and white, yes or no type answers. Nonetheless, a continuous linear program can be solved in polynomial time. And so the question we're going to explore is whether we can somehow use linear programs to help us solve or at least approximate solutions to integer programs. Okay. All right, so here's like the high level recipe that we'll be looking at today. Suppose I'm given some kind of discrete problem that we've written down as an integer program. So we'll look at set cover as a different example in a moment, right? But in general, integer program or some kind of discrete problem, okay, that I can express as an integer program. This is the thing I want to, maybe I can't solve because that'd be hard, but I want to at least approximate. The first step is to take that integer program and turn it into a linear program by just allowing x to be anything instead of just integers. So I want to solve an integer program. I can't solve it, but I can look at the corresponding linear program, right? They are similar. Everything's the same except now x can be any fractional value, not just the integer values, right? So we might hope that solving the linear program might give some hints or clues as to a good solution for an integer program. So that's what we do. We just plug it into a black box solver and say, oh, that takes polynomial time. In practice, there's very reliable software, right? So we'll solve the linear program with, I should mention there is also software for integer programs, so you can always at least try. They're a little bit more heuristic-y, but sometimes they do work. Anyway, okay, so given an integer program, turn into a linear program, solve the linear program, right? And we'll look at this and say, okay, I still don't know what the solution is to the integer program, but I do know the best possible solution to the linear program. Okay? So you might look at this and say, okay, is there any way that I can convert, a really good solution for a linear program into a pretty good solution to the integer program, right? Like, for example, if we were really lucky and the linear program just randomly output an integer solution, we'd already know it's optimal. That would be great. But in general, you might get some messy vector, with lots of fractional values. And you might say like, oh, if something is 0.99, I should just make it 1. That's pretty close. And maybe it's 0.01, I'll make it 0 or something, right? You can try like rounding or something like that. And there's really a very large space of different approaches you can take. I'm only going over one today, as sort of expose you guys a little bit to this style of thinking. So that approach we'll take today, well, it's going to be randomized rounding. But yeah, in general, you want to round your continuous solution to a reasonably good solution to the integer program. Okay. So all of our thinking today will occur in that last step. How do I take a fractional solution and make it into a good integer solution? Okay. All right, so now we'll just go through some examples and see this approach, this recipe in action. All right, so we'll do SAT first. I know you guys have seen this a million times before. So you're given some SAT formula, right? And you want to satisfy as many clauses as possible. Now, last time we did like 3 SAT with specifically 3 variables per clause. And today we're going to relax that to general SAT. So for 3 SAT, we showed that flipping coins will get you a 7/8 approximation. Right? That was the analysis. Right, so today we'll look at max SAT. The only difference this time is that I'm allowing for any number of variables per clause. Okay. So last time was exactly 3. Now there could be ones was 2, ones was 3, ones was even just 1, ones was 4, 5, stuff like that. Okay, so All right. Okay, so last time we really focused on, or a week ago, we really focused on this line. All right, for 3 sat, we just use linear expectation. For a single clause, we don't satisfy it only if like all 3 coin tosses came out bad, right? If it was, to remind us, the algorithm was for every variable, I flip a coin. If it's heads, I assign it true. If it's false, I assign it false. So if the clause was like x1, x2, x3, then I would have to get tails, tails, tails for the clause to not be satisfied. It's the only way not to satisfy it. So there's a 7/8 chance of satisfying any single clause. And then if I want to look at everything on average, then I can just use linear expectation and add everything up, right? Kind of simple. And amazingly, we can also de-randomize it. That's kind of fun. Okay, but it didn't have to be 3 sat, right? So if it was like 4 sat that had 4 variables, x1, x2, x3, x4, I would have to get 4 tails for it not to be satisfied. So the odds of satisfying something goes up from 7/8 to 15/16, if I did that correctly, right? So the approximation ratio goes up to 15/16, and so forth. Okay, so the funny thing is that, uh, for something like 2 sat, right? We even did, well, for exact 2 sat, we even have an algorithm for exact 2 sat, right? The approximation ratio actually gets worse to 3/4, right? And for k equals 1 sat, there's only one variable per clause. It's not very hard to get the best, algorithm for this. And we only get a 1/2. So this algorithm is actually kind of not so clever once k starts getting very small. Okay. Now, consider max sat, right? If I did our oblivious, very simple algorithm, flipping coin tosses for max sat, again, now there could be any number of variables per clause. What's the best approximation ratio I can guarantee? Seven, eight? As if it were 3 sat? Well, what if the max sat formula has some clauses with 2 variables? You're only getting 3/4 of that on average. So what's like the worst case? Half. So just based on this, I can't actually guarantee anything better than 1/2. Okay, so the best you can do is 1/2, which is, like plainly ridiculous, right? Because we're stuck on the case where basically k is equal to 1, which is like the dumbest thing. Okay. All right, so questions, can we do better? So we're going to try to do better following this recipe from before, or write the integer program, or write some integer program for it. Then we'll write an LP, or we'll just take the LP relaxation, solve it, and then figure out how to convert that into an integer solution. Okay, so, all right, let's just blank, see what you guys would come up with. So I'm looking at sat, okay, and I want to try to write an integer program for max sat. Okay, so just to get us started, the objective will be probably trying to maximize something. So I want to maximize the number of clauses I satisfy. So maybe what I'll do is, so I think there's m clauses, so I'll introduce m variables that have to be 0 or 1. Okay, so that's really saying they have to be integers and at least 0 and at most 1. And I say, okay, I might sum over all the clauses, right? So if I satisfy clause 1 or something and z1 is equal to 1, I get 1 point. Okay. Now, what we really have to do is we have to set variables to be true or false, right? So let me just like write that down. I'll make a bunch of variables. okay, where I interpret setting x1, to be 1 if I'm going to set it to be true, and false if it's going to be false or something like that. 0 if it's going to be false. Okay, so, all right, now we have to bind them together, right? Because right now the solution is just to set all the zi's to 1 and you just get m points or something. That's not very interesting. What we want to do is like, based on x, you should only be able to set zi to be 1 if one of the x's help you out, right? So for example, if I had a clause that looked like something like x1 or not x2 or x3, those are, oh, maybe I should change this a little bit. So not to confuse ourselves with the variables in the formula, I'll use y1s for the variables in the integer program. Okay, so the formula itself has x's, and each yi corresponds to xi. So yi is equal to 1 if I'm going to set xi to be true. Yi is 0 if I set xi to be false. Okay, so take a clause like x1 or not x2 or x3. I want to come up with some inequality that says, oh, I should only be able to set that clause to be 1. Like I get 1 point for the clause if one of those variables help me out. Yeah. Okay, yeah, so if this is like clause 1. All right, so you said z1 less than or equal to. Okay, we're using y's, but yeah. 1 minus y2 plus y3. Right, so in general, we want to make the z's as big as possible because those are the points, right? And this is saying, okay, if I want to set z1 to be 1, meaning I satisfy clause 1, then I have to either set x1 to be true, in which case y1 will give me 1 point, or I have to set x2 to be false, in which case y1 minus y2 will give me 1 point, or I have to set x3 to be true, in which case y3 will give me 1 point, right? So that's the idea. So we can sum over. In general, I can say like, oh, if I sum over all the variables where xi is in clause j, yi, plus the variables I where like xi bar appears in clause j, so I'm kind of making up notation, but hopefully it makes sense. 1 minus yi is greater than or equal to zj for all clauses j 1 through n. Okay, so for each clause j, we make that same idea. Okay, so now what the integer program will do is it'll try to choose x's so that it can make the z's as big as possible in total. Okay. All right, so, oh, that's not good. Yeah, okay. All right, so, okay. So that was the integer program. And the linear program would take that idea and do nothing but now relax from 0 or 1 to being between 0 and 1. Okay, so the only difference highlighted is that what used to be like the curly brace thing is now a square bracket because it's allowed to take continuous values. Okay. So now you can satisfy a clause by setting like x1 to be half true and x2 to be half true or something, right? 0.5, 0.5, something like that. Okay. All right, so putting these things side by side, right? They're very similar, right? I mean, like only like 4 symbols changed, or 4 characters changed from one to the other. But one is NP hard because the one on the left just captures maxat exactly, right? Setting it to 0 is just setting it to be false. Setting it to 1 is just setting it to be true. If you can solve the IP, you can solve maxat exactly. So that's NP hard. On the other hand, this continuous version, which did nothing but allow for fractional values, actually has a polynomial time algorithm, right? So just small change like has a world of difference from a computational complexity point of view. Okay? Now, one thing important to point out is that, integer program in this case is strictly just more restrictive compared to the linear program, right? So the integer program says you have to choose 0 or 1. And the linear program says you can choose 0 or you can choose 1 or you can choose any value in between, right? So anything that counts for the integer program would count for the linear program. Any feasible solution for the integer program is feasible for the linear program. Okay. So if you're trying to like maximize something, you strictly have more choices and more possibilities for the linear program. So the optimum value for the linear program will be at least the optimum value for the integer program, right? Like it doesn't hurt you to have easier constraints. All right. Okay, so now here comes the actual the kind of interesting question. The first few steps are, well, maybe it was tough because it was our first time to ever do it, but in general, with practice, kind of more straightforward. But here comes maybe the more conceptually tricky part. So you've solved the LP, right? And you have all these Y values, but they're not just 0 or 1. So they don't just exactly tell you what should be true or false, right? And our goal is to take these continuous values and turn them into discrete 0 or 1 or true or false assignments. Okay. So the question is, what are some ideas, right? At some level, it's a question of how do I interpret a fractional value? So I left this space open to see what you guys would come up with. What are some ideas for trying to convert a fractional solution into a discrete one? Okay. I like how you started that was the most stupid possible solution. So okay, so for yi, so the idea is for yi, uh, okay, okay. So that's one approach, right? I can treat each of these yi's as a fractional value and interpret it as a probability. Any other ideas? Well, one that's often suggested, maybe not this year, is you could maybe try deterministically rounding. So you might set xi to be true uh, if like yi is at least 1/2 or something, and then false if yi is at most 1/2, right? So this would be a deterministic approach where you just do one or the other. Okay, well, the first option is going to be what we're going to analyze, just randomly rounding one. And so at some level, yeah, what it's really saying is like I always think of like, I feel like in some English class or something in high school, we had some question like, what is half a chair or something? Like, I don't know, the Greeks thought about this or something. Like, what is half a chair? Because if there's two legs, it'll fall over. You can't sit in it or something, right? But this is sort of giving us an outlet to this question. You can say, oh, a half a chair is a chair that's there half the time, right? And that's what we're kind of saying. Setting y1 to be 1/2. Like, what does it mean for something to be half true and half false? Oh, it's going to be a random variable that's true half the time, right? So this is really important. This idea that, because we live in kind of a discrete world and we think in a discrete way. And what we kind of see is that probability is giving us one way to interpret fractional values, right? That don't, in situations where fractional values otherwise don't naturally make sense. So that's important. Okay, so that's what we'll do. For each variable xj, we'll set it to be true. Okay. All right. Okay, so let's analyze some stuff, right? So we want to figure out the probability of each clause being satisfied, and then we can add everything up and use linear expectation afterwards. So some particular clause Ci, the claim is that it's satisfied with probability at least 1 minus 1 over e times Zi. Okay. Okay, the constant will that 1 minus 1 over e will come up kind of randomly in our calculations. But I think the most interesting thing is the fact that the Zi is there, right? Our LP, that's like, oh, our LP is saying, oh, we fractionally satisfy the clause Zi times or something, right? And we don't quite get that. We lose a little bit. 1 minus 1 over e is like 0.68 or something like that. But it's something proportional to Zi, right? That's, I think, the real point of interest. Okay, so if I want to calculate the probability that I don't satisfy, or that I satisfy Ci, how might I get started? Yeah. All right. So let's try looking at the probability that I don't satisfy Ci, because in this particular case, there's many different ways to satisfy a clause, right? But there's only one way where we don't satisfy the clauses, which is where every variable is going the wrong way. It's a little bit easier to look at it this way. So, okay, so this you kind of need like all the coin tosses to go wrong way. So you need like, okay, so it'll be the product. So if I look at all the variables j, where like xj kind of appears positively in Ci, so it'll be like the probability that xj is equal to false, right? So for every, like, if x1 appears in a clause, x1 has to be false in order for it not to be satisfied, times the probability over all j's where the negation appears in the clause. So like if x2 bar is in the clause, then for the clause not to be satisfied, I have to have x2 equal to true. Okay, I know there's a lot of symbols, so just tell me, feel free to ask questions. Okay, good. So I've just kind of written out the only way for the clause not to be satisfied by, multiplying those probabilities together. It's like getting all tails kind of thing, right? And now we just need to plug in what are these probabilities, right? So for a particular variable xj, what is the probability that xj is equal to false? What is the probability that xj is false? 1 minus yj, right? Because it's heads with probability x, or it's true with probability xj, yj. And then what are the odds that xj is true? Sorry? Also 1 minus yj. So you're saying that the odds of it being true or the odds of being false are the same? They should add up to 1, because one or the other. Okay, yj. Right, so for each variable, x1 is set to true with probability y1. x2 is true with probability y2. Okay, here's equal signs. All right, here's the one thing that maybe you guys haven't seen before. Okay, so this is uh, Oh no, is that the best way? One sec, there's a trick here. No, no, okay. Okay, so, never seen before. Okay. All right, so, okay, so here's what's kind of going on, right? Uh, we're used to doing addition, I think. And looking at products, like what do we do from here, right? I'm multiplying a bunch of numbers together. Sorry? Oh, take the log. Okay, yeah, just give me a sec. Finish my speech. Uh, we're used to adding numbers together, and the linear program is used to adding those yj's together, right? Like if we add the yj's and 1 minus yj's, there's actually like some meaning from the linear program. The linear program doesn't directly tell us anything about multiplying them together. So I wish this was some kind of summation of yj's and 1 minus yj's, as opposed to a product. If there's a summation or something, I might be able to relate it back to zi because there's some stuff in the LP about that, but that's not the case. Okay, so I want to get rid of multiplication. You said I can take logs. Okay, if I did that, you get some e to the, uh, well, okay, exponentiate, and now you get like a sum. So I'm gonna take e to the log kind of thing because that'll cancel out. So you're summing over all these j's where xj is in the clause. Sorry, that should be an in. 1 minus log of 1 minus yj plus summing over all the things where negation appears, log of yj. Okay, so that's good because now, like in the exponent, I'm looking at some sum, which is great. I like sums, but I am also looking at a sum of logs, and I don't know what to do with that, right? The log of yj doesn't have as much meaning for us either. Okay, so that's one way to get rid of. There's basically two ways in the world to get rid of products and turn them into sums. One is logs, but here it's not going to help us. It did help us with that foreign exchange problem once. All right, there's a different way. I don't know if you guys have seen it before to try to convert a product like this into a summation. And it's not exact, actually. It's going to be an inequality. Oh, Cauchy-Schwarz? Not in this case, actually. That's a good guess. Who said Cauchy-Schwarz? That's always a good guess, but here it won't work. Yeah. Not the triangle inequality. Yeah. Sorry? Yeah, so there's this amazing inequality. Well, okay, so you guys might know that e to the x in general is equal to 1 plus x squared over 2 plus x cubed over 3 factorial plus x4 over 4 factorial and so forth. Okay, that will get you back the exponential function if you plugged in this never-ending polynomial. So like if you think like just for the sake of discussion, if x is really small, like x is 0.0001, right? Then that 0.001 squared is x squared is very small compared to x. X cubed is very small compared to x, right? So at some level, 1 plus x for really small values of x is a pretty good approximation of e to the x, right? For really small values of x, those smaller values, because they're squaring and cubing and going to the fourth, kind of disappear, right? They're relatively diminutive. Okay, now that's not the actual intuition. The inequality that we actually have, and it's like the most useful, silly thing in the world, is that for any value of x, 1 plus x is less than equal to e to the x. Okay, so that's like if I drew some kind of thing and e to the x is like a curve that looks like this, right? And it crosses the x equals 0 mark at 1, right? And then if I drew this line, this is like 1 plus x, it's underneath the curve. Okay, it's not too hard to prove. You can look at the derivative and stuff like that. Okay. So it seems like a very, very crude inequality. Okay, that 1 plus x is always at most e to the x. And certainly, for really large values of x, this is not a very good inequality. I mean, the gap gets ginormous, right? In fact, usually, like in the beginning of an algorithms class, we talk about how big a difference like an exponential is compared to any polynomial or whatever. I'm sure you guys have done this a gazillion times. Okay. But for very small values of x, there's not that big a difference between 1 plus x and e to the x. And taking this inequality, you lose some, but not too much. Okay, so let's put that in action here. So this applies for all x, even if x is negative. So 1 minus yj becomes e to the minus yj. Or at most, this is going to be a less than equal to. Okay? And, all right, what happens to this one? How do I apply the inequality to yj? Here, don't just do this. Like, what is it? E to the yj minus 1, which is the same as negative 1 minus yj, just to make it look a little bit like the first term. Okay? All right. Okay, so now what's great about this? What can I do now? Okay, so we put in the exponent. It probably doesn't look much simpler at the moment, right? All I did was like make the font smaller and put it in the top right corner. Like, it hardly seems like a gain. But now what can I do? Ah, was the, e to the x times e to the y is e to the x plus y, right? So I can do summations in the exponent. Uh, the only hard part about this is writing small. Okay. Actually, it might be helpful to put a parentheses around the whole thing and make that a plus sign. Okay. All right. Good. Right? Now at least I have, it's sitting in the exponent. It's a little bit annoying, but the thing in the top corner makes more sense. It has more meaning, right? Now what can I do? I'm trying to eventually get to the zi's. Yeah. Yeah, so we have this constraint. We have this thing. That summation, I guess you guys can't quite see it. That summation is at least zi. Okay. So this thing, uh, because it's, yeah, I change colors. Let me do this one. Is less than or equal to e to the negative zi. Okay, so this is like, uh, this is great because we're making some progress, right? I've started with the y's and I've ended with the z's. Okay. In fact, I started with a product involving the y's, and I had to introduce this one mathematical inequality, which you guys maybe hadn't seen before. But if you do this stuff enough, you just basically use this all the time and you get used to it. Um, and I'm now got something related to the z's. Like there's a little bit of meaning to this. Okay, so we're chipping away at it. Okay. I need more space. Okay, so I know it's a little bit more mathematical than maybe we'd like to do. This is the last bit though. Okay, so now I need to deal with this, right? This is still a little bit screwed up because e to the negative zi is a little bit hard to interpret. Okay, the claim is that we want to eventually show that this is at most like 1 minus 1 over e zi or something, because we're looking at the probability that ci is not satisfied, and eventually I want to get the probability that ci is satisfied. Okay, so, all right, so look at this function, f of x is equal to e to the negative x, right? So this is a convex function, right? If I kind of drew the xy kind of thing, So it's going to go the opposite direction, right? This is what it'll look like, right? But it's curving, it's smiling up or whatever. So it's a convex function, convex up, concave down, that kind of thing. Okay. So, okay, so let's see. E to the negative, all right, so, zi is maybe somewhere here. Maybe this is 1, this is 0, and this is zi. Okay. And you guys might have done this before, but if you draw like, oh no. If you draw a line, right, depending on how good my curve isn't like very exaggerated, but that blue line goes slightly above the purple. I don't know if you guys can tell, right? So I should have drawn it more, the purple more exaggerated, but if you draw like a line across a convex function, the curve is going to be underneath it. Okay? So what does that mean? So this point that's kind of like above it here, this would be like zi times e to the minus 1 plus 1 minus zi. Oh no, I got this backwards. E to the 0. Yeah. Okay, so, right. Okay, so it's always the case. So you always have something like, okay, so now if we put that together, we get e to the minus zi is at most 1 minus zi e to the 0 plus zi e to the minus 1. So this is just a convex function, kind of the line, the average of the 2 points being above the f of the average kind of thing. Okay. And, all right, e to the 0 is 1. So what do we get? We get something like, you guys can tell me if I'm wrong, 1 minus 1 over e zi. So just to remind you, e to the minus 1, of course, is 1 over e. Okay, so we add that together. All right, so we had to do a little bit more math than we're used to. In particular, we used this inequality, 1 plus x is less than or equal to e to the x, and we had to use the fact that e to the x is a convex function as well. So we had to do some inequalities. We've never really done that before. Okay, but I think that'll be the limit in this class. Okay. But in conclusion, what did we do? We started with the probability that you don't satisfy Ci, right? And we concluded, well, there's an inequality in here, right? We got to that point. That means the probability you do satisfy is like the 1 minus the whatever. So you get at least 1 minus 1 over e zi. Okay, so there's a little bit more math than we were used to. But I think it'll still give you some flavor of the game, right? So we look at the probability and there's like an experiment, right? I interpret the LP solution as flipping these coins, okay? And then I have to figure out how to relate the LP solution back to the actual z's, right? So the sum of zi's, the zi's are what I'm looking for because that's related to the objective. So we have to do like, a little bit of math that we're not used to. If you do this a lot, you realize you only use the same 3 tricks, so it's not as intimidating. Like you just kind of keep doing this, but the first couple of times it's a little much. You put it all together, and at the end of the day, we get something that's easier to interpret. We get something related to the zi's. Okay, so that's what's going on. Okay, all right. So now this part, I think you guys can guess more easily. So we showed that any particular clause is satisfied with probability at least 1 minus 1 over e zi, where zi is that value from the LP. And so now the question is, the claim is that the expected number of clauses I satisfy is at least 1 minus 1 over e times the optimum value. The optimum value might not be 100%, right? It may only satisfy, the best solution may only satisfy some clauses. All right, so how do I do this? Okay, linear of expectation. So this is at least summing over the clauses, the probability that satisfies CI, right? So that's linearity of expectation, which we did a week ago. And so for each clause, we can plug in the thing which was a little bit messier, but nonetheless, we were able to show, okay, 1 minus 1 over e times z to the I, or z sub I, right? And now how do I do the last step? Yeah, so if I rearrange this, I put the 1 minus 1 over e on the outside, right? This is the objective from our LP. So this is at least a right opt LP because it's the optimum value from the LP, right? The linear program. LP is short for linear program. And the linear program is going to do at least as well as the best discrete solution. So maybe to make it clear, I'll write opt SAT or something, the actual optimum for SAT. Okay. All right. So that is it. Okay. So it is true that this claim up here was a little grungy, but the main idea is, we do some random experiment based on the LP. We fight through a little bit of math, or you find a friend to fight through the math for you, and then eventually you're able to relate things back. And in particular, we appeal to the fact that those ZIs are intimately connected to the optimum value for the original problem, right? So the LP also gives us a certificate for the optimum value of, right? So like if I do the random experiment, right, and I want to say, oh, did I actually get a good solution or not? I can look at how many, so I flip the coins and I satisfy some clauses and I count them up, right? And I can compare it to the optimum value from the LP, right? And say, oh, I did get at least 1 minus 1 over e times the LP off. So you actually have a certificate from the linear program. It may be higher than the true discrete solution, but it still gives you some basis of comparison. So I can argue that I get at least some fraction of the optimum value, even though I don't know the optimum value, right? These are NP hard problems. I don't know the exact optimum value, but we've proven something to guarantee I get at least some chunk of the optimum solution. Okay, so in general, for a lot of NP hard problems, we are interested in the problem, we don't know how to solve them, but we don't really want to give up rigor just because they're NP hard. So we try to do this kind of thing where we prove that, oh, okay, we get kind of close to a good solution. Okay, so this is just like one example for one class, but there's a whole field. Okay. All right, so now the next question is, can we do better? Okay. All right. Now, we show that a particular clause is satisfied with probability 1 minus 1 over e zi. Right? We have to use that inequality, 1 plus x less than equal to e to the x. And, we have to use some inequalities, and those aren't exact, right? It's just a less than equal. So we might have lost a little bit of kind of value. Okay. Now, let's look at some special cases. What if the clause only had one variable, right? So what if ci was just one variable x1, right? In which case, it flips heads with probability y1 or something, right? So so in general, it's 1 minus 1 over e zi. But if the clause I only had one variable, what would it be? For simplicity, for concreteness, let's say that ci is equal to just x1, right? Just one variable x1. Okay, so the probability we satisfy ci will be I guess y1 here. It's variable x1, right? And how would zi be related to y1? So the LP is going to want to make zi as big as possible. So it'll probably set it to what? It'll set it to y1. Okay, so zi will be equal to y1, right? So that's much better than 1 minus 1 over e times z1, or zi. We just get zi, right? Okay. All right, so now what about two variables? Let's say that ci is equal to x1, like x1 or x2 for concreteness, right? So we can kind of retrace the same steps. The probability that I satisfy ci is, or maybe let me do it differently. All right, the probability I don't satisfy ci. Okay, so ci just has two variables, x1 and x2 for simplicity. What is the probability that I don't satisfy ci when I kind of do coin tosses based on the y's? Right? Okay. Okay. Now, last time we did like, oh, and this is at most e to the negative y1 and stuff like that, right? Okay. But for two variables, you can actually do a little bit better. Anyone know inequalities for dealing something with like a times b? Oh, okay. So that's called, name? MGM, AMGM, the arithmetic mean, geometric mean inequality. So this is like, you have some amount of fence. What's like the most area you can surround the fence with or something? Okay. All right. So, what is this? Like a times b, it's really square root, is less than or equal to a plus b over 2. So the geometric mean is at most the arithmetic mean. Okay, so if I apply that here, we'll get 1 minus y1 plus 1 minus y2 over 2 squared. Okay. Now, y1 plus y2 is actually probably equal to, but it's at least zi, right? So I get like 1 minus zi over 2 squared. Okay. And then, right. Now I can do the same convexity trick as before. So the function, where do I have space? Forgot how much math this lecture would have. Anyway, the function f of x, which is equal to 1 minus x over 2 squared, which is sort of where zi sits. That's also a convex function. So I can do the same, like the line goes above the curve inequality that we did earlier, which would give us 1 minus zi times the value at 0, 1 minus 0 over 2 squared, plus zi times the value at 1, 1 minus 1 half squared. We're out of space again. Okay. And, okay, I'll just do the math and get it over with. This should be equal to, so this is a 1. So I get 1 minus zi plus, that'll be 1/4, so zi over 4th, which is 1 minus 3/4 zi. Okay. So you put that all together, that's the probability I don't satisfy CI. So the probability I satisfy CI when there's only two variables is at least 3/4 times ZI. Okay. All right, so what's that saying? So these are both slightly better than 1 minus 1 over e. Again, 1 minus 1 over e is something like 0.68 if I'm not mistaken. It's something a little bit less than 3/4. Okay, so in general, those inequalities, they work fine. We got 1 minus 1 over e, but for those really small cases where k is equal to 1 or k is equal to 2, you can look a little bit more closely and you can do a little bit better, right? Especially k equals 1, you can get 1, so that's good. And then k equals 2, you can get 3/4. That's a little bit better. Okay. All right, so let me put this like side by side, right? Like if I looked at clauses based on how many variables are in them, right? So on the oblivious side, it's like 1/2, 3/4, 7/8. That's what we did last time. And for the LP side, the LP based approach, we get at least 1 minus 1 over e for everything, but we just showed for the special cases of k equals 1, you just get zi. And in the special case k equals 2, you get 3/4 zi. Okay? And if you look at it closely, for each of these, like the average, like 1/2 and 1, the average is 3/4, right? And on the second line, 3/4 and 3/4, the average is 3/4. The third line, 7/8 and 1 minus 1 over e, if you calculate it, the average will be actually over 3/4. Okay, so you're actually kind of like on average getting at least 3/4 zi between the two approaches. Okay, so this is like kind of so what I'm saying is this: we have right now the best approximation factor we have is 1 minus 1 over e, right? But for any particular k, sort of the average of two different approaches gets 3/4 approximation, which is better. Okay? So the question is there anything we can do to sort of get the best of both worlds? Right? So I have kind of two different algorithms. One is to completely randomly flip coins. The other is to solve the LP and round according to the assigned values, right? And is there any way to somehow mix them, right? Because it seems like, for example, the LP does really well when k is equal to 1 and k is equal to 2, especially, right? Because then it's getting like 1 and 3/4. While the oblivious approach is much better when k is big, right? 7/8, 15/16. So they have different strengths. So is there any way I can kind of combine the two algorithms and sort of get the best of both worlds and try to get a 3/4 approximation, right? How can I combine those two algorithms and get a 3/4 approximation? This one you guys might be able to guess, right? You have two algorithms. They have different approximation behavior. I want some kind of hybrid algorithm to sort of get the best of both worlds. I want to try to get a 3/4 approximation for SAT, max SAT. Yeah. Okay, the suggestion was sort of at a high level, can I run the LP on the small clauses, right? So maybe an idea is like, oh, let me look at only clauses with one or two variables because those are the ones that the LP does well. And I'll make a smaller linear program with fewer clauses in it. And that'll give me a bunch of Y values. And I'll randomly round those. And then I guess everything else I'll obliviously round. But that's an idea, right? Can we do the small clauses first or something? But one issue, right, is that, okay, I'm only looking at the small clauses, but I am still looking at all the variables, right? So even just worrying about the small clauses, I'll end up rounding all the variables. So even though the big clauses are left over that I didn't look at, I don't have any variables left either. That makes sense. At least in that version of that algorithm, right? So it seems hard to do one before the other because both algorithms assign values to all the variables. That's kind of an issue that comes up. How can I get the best of both worlds? How can I combine these two algorithms? Yeah, how do you algorithmically take the average of two algorithms is another way to think about it. Right? It's an interesting conceptual question. Sorry? Okay, I can solve the LP with everything you're saying. And then let me just say, I think what you said verbatim, take the values corresponding to the small clauses, one or two variables, round using that, and then deal with everything else later. Okay, but again, if you think about what the algorithm does, okay, so we solve the LP, we get everything, and the values, so the algorithm itself only looks at the yi's. The analysis was based on the z's, but the algorithm itself just looks at the y1, and flip heads is probability one y1, and looks at y2 and flips heads is probability y2. So the algorithm only looks at the y's, and so in your algorithm you would still roughly do the same thing, right? So even though you're only looking at small clauses, you may still be looking at all the variables, all the yi's. So you'll still end up flipping all those coins based on the yi's. Does that make sense? Yeah, so what if all the variables are in some of the small clauses? Like, suppose every variable is in at least one small clause. Then it would be the same, right? Okay. So, yeah, the question is tricky, right? It's not clear. Any other ideas? Yeah. Okay, so if I took the average of 1 over 2 and y1 for each one, how would I analyze that? Yeah, one thing kind of hard is that, yeah, okay, yeah, how do I take the average of two randomized algorithms? So, okay, can I just make the clauses bigger? Well, okay, I'll give two answers. One, if that were allowed, why would you even stop at one or two, right? I would make all the clauses super duper big and then just run the oblivious algorithm, right? Because the oblivious algorithm is even better for bigger clauses. I would make the clauses infinitely big and then there's no way you get any clause wrong. But what would you actually do? You'd introduce all these fake variables and you'll get the clause right because your fake variable came out to true. But satisfying a clause with a fake variable doesn't help you satisfy a clause with the real variables at the end of the day. So you're just cheating, I think, as far as I can tell. It's just too convenient. Okay, well, I think I've milked this for all it's worth. So okay, here's how. Yeah, you have one more idea? Okay. How do you take the average of two algorithms? Okay, we're gonna flip a coin. If heads, I'm gonna run the oblivious algorithm. If tails, I'm gonna run the fancy LP algorithm. Okay. And the key point is that because I'm only interested in the average, the expected number of clauses satisfied, I'm going to show that this does well on average, and that's all we need. Okay? All right, so this is I love this. Okay. All right, so that's it. That's the only trick. I'm gonna flip a coin and then choose one of the two algorithms. Okay. In some ways, this is much simpler than trying to. I mean, you guys had more sophisticated approaches, like oh, try to do small clauses first and then the rest later. Like that's it's getting more. This is kind of dumb, right? I think we can all agree. Okay. All right. So, all right. So now, how do I analyze this, right? And I'll keep it moving fast because we're about out of time. So let's say that CAI has K clauses. Let me pick one that's maybe, well, any row would have been fine. Okay, so, okay. The probability that I satisfy CI, right? And then we can look at the two situations conditionally, right? So I can say, oh, what's the probability uh, that I satisfy CI given that it flipped heads and we did the oblivious, times 1/2, because that's the odds that I flip heads. Okay. Plus the probability that I satisfy CI given that it flips tails and I do the fancy LP approach, times 1/2, because that's the odds that I flip tails and do the fancy LP approach, right? So let's say that, okay, so this thing is at least, all right, what do we know? 1 minus 1 over 2 to the k is what we got, right? Like when k was 3, that's 1 minus 1/8, and we get 7/8. Times 1/2 plus, depending on the value of k, it was either 1 or 3/4 or 1 minus 1 over e, right? If k is equal to 1, k is equal to 2, or k is at least 3, times 1/2, right? So what we see in this last part is exactly taking the average of one of these rows of the table, right? The average of 1/2 and 1, or the average of 3/4 and 3/4, or the average of 7/8 and 1 minus 1 over e. Okay. So for any value of k, you're going to get at least 3/4, right? Now any clause is satisfied with probability at least 3/4. So by linear expectation, you'll get at least 3/4 of the clauses on average. Okay, so it's a fun way to leverage randomization. So that was fun. I think it was fine that we spent time talking about max set because it's fun. I would have otherwise also talked about the set cover problem, where there's also a classical algorithm based on randomized rounding. You write the LP, and then you decide whether or not to take a set randomly, flipping a coin. Okay, so I encourage you to check out the notes, but I won't keep you here any longer. All right, thanks, guys.